Complex Shapes, sponsored by Outokumpu and hosted by Metal Forming Magazine. My name is Brad Kuvan. I'm the editor of Metal Forming Magazine, and I'm pleased to serve as your moderator for today. Since today's go-to-meeting session is being recorded for archiving, all participants are in listen-only mode. The speaker and other listeners will not be able to hear any audio from your site during the program. However, you do have the ability to communicate with us throughout the program by submitting any questions using the question box, which is located in your right-hand control panel. Simply type your question to an organizer as selected from the drop-down menu. While we don't intend to interrupt the presentations to pose your questions to the speakers, we do recommend that as questions arise during the presentations, you go ahead and jot them down in the Q&A panel. We'll hold all questions until the end of the presentation. Lastly, I want to let everybody know that a link to the recording of the webinar will be available within the next few days. It'll be archived on our website, and we'll send you that link once it's posted. Now it's time to begin today's webinar. Joining us today as presenters are representatives from Outokumpu, as well as two Outokumpu customers who will share their experiences fabricating duplex stainless steels. First, Gary Carinci, a technical consultant with Outokumpu, will provide an overview of duplex stainless steels and their properties, as well as recommended procedures for forming and welding duplex stainless alloys. The discussion will also address the potential cost savings derived when using lighter gauges of lean duplex over standard austenitic grades. Outokumpu produces duplex stainless steels in plate, pipe, bar, and other products from 16 mills around the world. Gary will then introduce Michael Mulhern, founder and president of Outokumpu customer Tri-Pyramid Structures, for a case study presentation on a very unique fabrication project that I think you'll find extremely interesting. Tri-Pyramid designs and fabricates one-of-a-kind architectural products ranging from yachting rigs to floating staircases. Then we'll enjoy a second case study from Outokumpu customer PVI Industries, a fabricator of water heaters for commercial and institutional applications. Joining us today is PVI President Chris Bolus, who will describe how his company cuts, forms, and welds duplex stainless steel products. Then we'll wrap up with a summary discussion from two members of the Outokumpu commercial team, Michael Obanoff and Jim Leiner. Finally, please note that redistribution of the materials from this webinar is strictly prohibited without written consent, and that the information contained here is for information only, with no assumption of liability by Outokumpu and its affiliated companies. Okay, with that, it gives me great pleasure to welcome Outokumpu technical consultant Gary Carinci. Gary?
Thank you very much. Good afternoon, everyone. The first thing I want to do is start out with a brief explanation of the grades of stainless steel. The most common grade of stainless steel is the austenitic grades, such as 304, 316 stainless steel. And then we have the ferritic or 400 series stainless steels. Today we'll be talking about the duplex grades of stainless steel, which are a combination of both the austenitic and ferritic stainless steels. When we look at the duplex stainless steel, it's comprised of approximately 50% austenite and 50% ferrite, as shown in the micrograph. Duplex stainless steels combine the beneficial properties of both austenitic and ferritic stainless steels, and this includes the high strength as well as high resistance to stress, corrosion, cracking. We look at the characteristics of duplex compared to standard grades. They have higher strength and fatigue resistance, as well as good corrosion resistance and corrosion fatigue. The service temperature range of duplex stainless steel was -40 to 600 degrees Fahrenheit, which is similar to that of ferritic stainless steels. These properties result in a cost-effective solution for high-strength construction and resistance to pitting and crevice corrosion resistance. We look at the history of duplex stainless steels. It's not a new invention. They were first introduced in the 1930s by Outokumpu's Avesta, Sweden Stainless Steel Works. But modern melting technologies have enabled lower carbon chemistries, and this has led to the development of new duplex grades. We look at the brief history here of duplex stainless steels. The standard grade 2205 was developed in the 1970s. The super duplex grade 2507 in the 1980s. Then the lean duplex family, or LDX family, was introduced in the 2000s. These grades have lower nickel contents and are more cost-effective compared to other duplex grades. In 2013, the formable duplex grades FDX 25 and 27 were developed, as well as EDX 2304, which is an enhanced version of the 2304 grade. The duplex grades now are a fairly large family with different versions. Here you can see consist of the standard grade 2205, but we now have the lean duplex, enhanced duplex, formable duplex, super duplex, and hyper duplex grades. So there's many different types of duplex stainless steel depending on the application. Duplex grade compositions are compared to the standard austenitic compositions 304 and 316L near the bottom of this table. What you can see is duplexes have higher chromium and nitrogen contents, but lower nickel contents in 300 series stainless steel. The lower nickel contents result in a more cost-effective alloy. Also shown is the PRE, or pitting resistance equivalent. This is shown in the table and can be used to rank the corrosion resistance of stainless steels. The PRE is calculated as the percent chrome plus 3.3 times percent molybdenum plus 16 times the nitrogen content. The higher chrome and nitrogen of the duplex stainless steels result in the high levels of corrosion resistance. The figure in this case shows the duplex grades have higher yield strength than the corresponding austenitic grades towards the bottom of this figure. You can see at any given corrosion resistant level, we're always going to find the duplex have higher strength. This is a slide basically summarizing the formable duplex stainless steel concept. We look at this, the figure on the left shows the new formable duplex grades FDX 25 and 27. And they have higher elongation compared to other duplex grades. The elongation is similar to that of the austenitic grades in this figure. If we look at the figure on the right, it shows that the corrosion resistance and elongation of FDX 25 and 27 are similar to that of 304 and 316L stainless steels. If we now look at the plot of stress versus strain behavior and look at the 0.2% offset, it illustrates that duplex has higher yield strength than both carbon steel and 304 stainless steel. The yield strength of duplex is approximately twice that of 304 stainless steel. When we consider structural applications and potential weight savings, specific strength applications where there's a strong influence of strength, such as pressure vessels, storage tanks, and piping systems, this offers the best opportunity to use thinner gauge duplex products. We're looking at specific modulus applications related to the stiffness or rate ratio, such as beams and columns. We have less of an opportunity for weight savings in those type of applications. Next, we have the physical properties of duplex, and here we compare duplex versus carbon steel and 316 stainless steel. This table shows the coefficient of thermal expansion of duplexes between that of carbon steel and 316 stainless steel, and the thermal capacity and electrical resistivity are similar to austenitic stainless steel, but higher than carbon steel. Next, going to move into a brief discussion of fabricating with the duplex stainless steel grades. If we look overall at fabrication, duplex stainless steels can be used for many forming applications. Be used for stretch forming, drawing, spinning applications, but the one thing you do find when you work with these materials is the high strength can cause a relatively high spring back effect, and down gauging in these applications where you're using less force can reduce this effect. We look at the machinability. The machinability index in this plot increases with improved machinability. The chart shows that the machinability of most duplex grades is more demanding than 316L. However, LDX 2101 has shown excellent machinability compared to 316L when the appropriate machining parameters such as cutting speed and cutting depth are optimized for this grade. When we look at formability in general, we can see there this is mainly draw formability. We can see that the forming characteristics are going to be somewhat less for duplex when we compare them to austenitic materials. We also have higher spring back, again, as we mentioned, with the higher strength materials. If we can take advantage of down gauging, going to thinner materials, these effects can be minimized. We look at cold forming. It's going to be similar to some of the other forming we talked about. You're going to end up using larger radiuses to bend things. Again, more spring back for a certain thickness when you compare it to 300 series stainless steel. So you're typically going to require more power when you do cold forming of duplex stainless steel. When we look at hot forming, we'll go over some of the temperatures in the next slides. The thing about duplex, though, materials are very soft at high temperature. They have to be supported in some cases when you're doing heat treating in furnaces. Otherwise, you have large distortion effects. Typically, when you're done hot forming, you need to quench the material. Basically, below 900 degrees C, you want to be quenching the material after hot forming or heat treating the material. These are some of the characteristic heat treatment temperatures for hot forming, quench annealing, and stress relief annealing. You can see the risk of embrittlement for these materials. Basically, you don't want to expose them to the 900 to 350 degrees C range. You have different things precipitating out that affect the fracture toughness as well as corrosion resistance at these temperatures. When we look at welding, all the typical stainless steel welding methods can be used. The one thing you want to be sure with welding duplex is you want to use the appropriate filler metal. In all cases, you want to try to use a filler metal. Again, the object here is to maintain the austenite-ferrite balance, and that's only done when you use the correct filler metal when welding duplex stainless steel. The microstructure in duplex stainless steel is controlled by two main factors. It's basically chemical composition and then cooling rate during welding. And we talk about composition. We're looking at the composition of the base metal as well as the filler metal. And then during welding, the way we control the cooling rate is through the inner pass temperature that we use on multiple pass welding as well as the heat input. We need to control the welding current, voltage, and speed. Those are all the inputs for the heat input. And when we weld duplex stainless steel, typically going to use a wider root opening as well as a wider bevel angle. The duplex filler metals, you're going to have less penetration. You're also going to have reduced fluidity with these type of filler metals. So these changes have to be made in the weld joint geometry. Temperature effects, I mentioned this earlier, why we want to make sure when we get below 900 degrees C the material is quenched. Between 600 and 900 degrees C we have the potential for intermetallic phases. We got in the 500 to 850 degrees C range. Now we have nitrides and carbides that can precipitate. And then from 350 to 525 we worry about ferrite decomposition into alpha prime. So again, you want to reduce the time at temperatures in these temperature ranges. And again, the reason is we want to keep the good corrosion resistance and toughness of the weld heat and the heat affected zone and the material by rapidly cooling. Some general welding recommendations. Duplex stainless steel typically does not have to be preheated before welding. If you're looking at interpass temperatures, they generally want to be 150 degrees C maximum. Again, we want to use appropriate filler metals. Really the only duplex where you can sometimes not use a filler metal and do autogenous welding is with LDX 2101, and that's typically light gauges and a single pass weld. For the heat inputs for the various duplex stainless steels that are shown here for the heat input ranges, if we're following the correct heat inputs and we're using the right filler metals, we should not need to use a post-weld heat treatment after welding. Nitrogen in the shielding gas as well as the backing or purging gas is strongly recommended for GTAW or TIG welding. For duplex stainless steel, nitrogen is an important alloying element, and we tend to lose that when we use this welding technique. So we need to use some nitrogen in both the backing and shielding gas if possible. When we're using GMAW, pulsing is advantageous, and some of the typical shielding gases are argon with 2%, oxygen, argon with 3% CO2, as well as argon, helium, CO2 trimix gases. Some more tips for welding stainless steel in general. And this goes for not only duplex but other grades, austenitic grades, special grades. You want to use the right filler metal, as I mentioned earlier. It's got to be appropriately alloyed for that grade. All stainless steel welding, you've got to control the heat input as well as interpass temperatures. The right joint type has to be made, whether it's a V-type joint, an X double joint. Those are all considerations, and they really depend on the thickness of the material. We're going to have to increase the joint angle and the root gap when we're welding special grades as well as duplex stainless steels. And with any stainless steel welding, again, it's very important to clean before welding. Typically, you want to use something like acetone or ethanol that's going to clean the surface and then quickly evaporate so we don't have any weld contamination. The other thing is the appropriate shielding and backing gas. We should have minimal heat tint. Here you see in this slide what happens when you go to lower 10 ppm's oxygen on the right. We have very little heat tint. So these different colors represent oxygen contamination during welding. So we want to achieve very low oxygen levels if possible, so we minimize the heat tint. If we do get heat tint, we're going to want to either remove that by chemical means such as pickling or by mechanical methods. The importance of post-weld cleaning. First of all, we want to use stainless steel tools. Basically, with post-weld cleaning, we want to restore the corrosion resistance. We can use mechanical means as shown in this slide at the top. Chemical cleaning such as pickling with acids. And the optimal process is actually removing it mechanically and then finishing it off with a chemical process as pickling. And this slide shows the difference between brushed and pickled and then the untreated surface with the heat tint. And why do we want to remove these heat tints? Basically, if you look at stainless steel before welding, you've got a passive film that's 2 to 5 nanometers thick that is enriched in chrome oxide. That basically protects the material, keeps it corrosion resistant in stainless steel. When we do a welding operation, we create a high temperature oxide. That oxide on the surface is very high in chromium. Under that is a chromium depleted layer that has low corrosion resistance. Again, some of these, sometimes the chromium level is less than 10%. So we want to restore the corrosion resistance after welding. We need to remove the weld oxide as well as the chromium depleted layer. Again, we do that either by through mechanical means or chemical means or a combination of the two. I'm now going to hand this presentation over to Michael Mulhern, who will discuss the Star Spangled Banner sculpture.
Thank you, Gary. My name is Michael Mulhern, and I am president of a company called Tri-Pyramid Structures in Westford, Mass. And we manufacture, design and manufacture all manner of architectural components for buildings around the world from a wide variety of materials. Our background is in manufacturing for the marine industry, in the nuclear submarine industry, in design and manufacture, and of all things, titanium mountain bikes. What I want to talk about today is our use and choice of 2101 for a project in Washington, D.C. at the Smithsonian. Our firm deals in a lot of different materials. On any given day, we may be dealing with titanium that's embedded in glass, 2507 duplex handrails that need very, very high strength and corrosion resistance, all manner of stainless steels, a lot of austenitics, but an awful lot of grades that are higher than that. And in this project, which I'm going to show you, if I get the slide to go. There we go. Big delay here. I'm sorry. I will try to be more patient. On this project right here at the Smithsonian, what the client wanted was a sculpture that was supported on the left-hand side of this slide on a giant bracket and cantilevers everything off to the right. The unit's quite large. It's 50 feet long. It supports some glass and plastic panels that have a mirrored surface on them. And the idea is this is to be an entryway, an entry marker to the Star-Spangled Banner Room at the rehabilitated Smithsonian. The project itself had a fairly long design period where we got to work through materiality and design, and one of the things that became clear through a lot of design analysis is that the lighter the material is on the cantilevered section of the flag, the easier the unit was going to be to build and fabricate. So high strength, or higher strength than an austenitic, something higher than 30 KSI yield, fairly highly desirable. Unfortunately, the budget was limited, and so we found ourselves in a place where, while we could have used an exotic, we couldn't afford to use an exotic. So in this case, 2101 represented for us a fairly good intermediate spot. The 2101 alloy is all of the curved elements that you see here on the flag. The flag is, in these photographs, has already been built. It's laying on the ground at the Smithsonian waiting to be erected, and then in the bottom left, the flag frame, which we built, has been erected, and then the panels are partially on in the next slide. For us, we have worked a lot with 2205, 2507. This was a fairly early adventure for us in 2101. We found that this guide was quite helpful in terms of fabrication guidelines for the duplexes. We refer to it fairly frequently, so I highly recommend this one. The fabrication itself involved everything: machining, cold forming, welding. The basic material was round bar, which we ground to a polish, mirror polish, before we did anything to it in order to bring it back. One thing Gary did not talk about is that the material finishes quite well. It finishes and polishes as well, or a little bit better than the austenitic. And what we have found is that if it's finished to a mirror, its corrosion properties are equal to any of the austenitics 316. Not quite as much. It will stain a little more, but not much. What you see in this slide and the next slide are components that have been cold formed, so rolled, cold rolled. It has a bunch of spring back. Make no mistake. But you can dial it in. You can, once you get used to it, you know what it's going to do. It's no different than any other stainless. You'll see down in the bottom left-hand slide that some of the units, the flat units, have been welded up. I'll talk in a minute about the welding procedures. You do need to pay more attention when you're welding this material than when you're welding a straight-up austenitic. The picture on the bottom right shows you units that are on the fixture getting ready to be welded one section and the next, and you can see the broader weld prep than we might normally use for an austenitic. Welding of the 2205 and the 2101, as Gary said, it wants to be clean. You can avoid pitting, you can avoid little inconsistencies in the weld by just enforcing that your welders are cleaning the material well. The inner pass temperature, 300 degrees F or 150 degrees centigrade. You need to monitor this. The guides all say that you do not want to spend a lot of time going through the transition. You need a quick cool. You also need to get down to this inner pass temperature. So our welding practice with both of these alloys involves heat sticks. It involves somebody with a clipboard actually monitoring the welding. Argon shield, we had on this project did not use nitrogen as an adder. I might in the future, having learned that from Gary today. Forced air cool, a lot of air, try to get it through the critical zone fairly rapidly. And as I said earlier, I'll show you in the next slide, we did work to minimize the time at temperature and get down to the inner pass temperature. We found, contrary a little bit to what Gary was saying earlier, we use a high heat input per pass, and the large beads worked well for these rounds. I think it's probably a bit of a personal preference thing. That's what our shop likes to do, and we found it worked fine in this application. And the results, and we did a bunch of testing for the client, are great ductility, great strength. There's little or no hot cracking. I don't think I've ever seen either of these alloys hot crack. And the lack of distortion is a huge bonus. When we work with the austenitics, we have plenty of distortion problems, and this material behaves much more like a straight-up carbon when we weld it. Sure why I can't get this slide. Jim or somebody, can you pick up this and try to go to the next slide? I am not able to. Thank you. I'm just going to say next, if you can just hold on to it. So phase change, time and temperature. This graph comes out of that manual I showed you a moment ago. And what it's telling you, I won't bother you with trying to zoom in on it, is that we need to maintain, to pass through that 900 to 300 C degree range quite quickly. We limit time at temperature to a matter of minutes in any of these welds. And it depends on how big the weld is, how hard that is to do. Some of these bars were 1.5 inches in diameter, and so we had a fair amount of monitoring to make sure we kept the time and temperature correct. So here you go. You see units ready to go, ready to be welded. The slides on the left were our raw material that's before we're into subframes. We have very little space. I think it's probably only a 1/16 of an inch gap between these. It welds fine. It welds nicely. It doesn't move around a lot. Cleanliness, it cleans up nicely. It's when you see here in the next phase, these welds are done. This is before any cleaning has been done on these welds. There's been no paste, no chemical used on these welds yet, and you can see it welds quite cleanly. These welds will all be fully ground and fully mirrored before the project is completed, but you can see here that it welds and cleans up quite nicely. Here it is in the fixture. The fixture itself was very high precision. And in order to get the panels in the right place, in order to keep the horizontal lines truly horizontal, every every single hanging point, every single fixture hanging point was precisely located. The huge worry in this project was that when we pulled it out of the fixture, it was going to spring. We have a fair amount of experience with the duplex alloys. You know, it doesn't move very much when you weld it, but it was still a huge worry. When it came out, they barely moved at all. The unit itself, that big giant frame, was cut here, and you can see in the upper right, cut in 4 pieces and split up so it could be moved across the road, moved from our West Coast facilities to the East Coast facility, or to the Smithsonian on the East Coast. In the bottom right, it's sitting there refixtured and getting ready to be welded back together again. TIG welds easily, so you know, TIG welding in the field didn't require any particular no difficulty, no particular materials. As I said, it finishes real nicely. It finishes cleanly, and you know, in this project, it worked out quite well in terms of both the economics. It's relatively cheap to buy next to the other duplexes, and it works without a lot of extra cost. So for us, in that project, it was a huge help. We also use it in some of our other architectural applications. These photographs here are a variety of complex glass and stainless steel stairs that we build for Apple Computer in their flagship stores around the world. These stairs use duplexes. They use 17.4 pH, a bunch of 304. They're inside. And so we don't have to usually go to the 2205 material for corrosion protection. We do occasionally use it for availability reasons, but for the most part, in these high-end stairs, we go ahead and use the 2101 alloy. The alloy itself, in addition to welding well, we machine a lot of it for these applications, and when we machine it, you know, our experience with it is slightly different than what Gary said. We're going to have to play with it some more. We tend to machine it a little slower than Type 304. We've had the best results with that. But given encouragement from Gary, I think we'll try to crank up the feeds and speeds and see what happens. In any case, it machines better than 2205, considerably better than 2205, and way, way better than 2507 if you're used to welding in that or machining in that. You know, and it's stable. It's nice and stable. When you cut it, it doesn't move very much. You know, we've had great luck with it. This is a project. This next slide. Come on. In Toronto, Canada, where the unit that you see silhouetted right there is all 2101 rather, for strength reasons. That was a combination of cutting, welding, and machining. There were quite a lot of those plates, and it really worked out quite well for us. So, you know, in closing, we really like the material. It has, you know, it has its place. It has, you know, amongst the arsenal of alloys that we use. So that's about what I have to say about it. I'm going to turn this over to Chris at PVI, and thank you very much.
Okay, thank you, Mike. Yeah, I'm Chris Bolus, president of PVI Industries, and PVI is a manufacturer of commercial water heating equipment, and our Aquaplex brand really starts with the LDX 2101. Our water heaters are rather large in size. Their typical customers would be schools, universities, correctional facilities, hospitals, hotels. If there's a large collection of people that are needing hot water at one time, good chance PVI is somewhere in the mix. If ASME construction and everything that we manufacture does meet ASME requirements, we do have an opportunity to make some very interesting shapes. What you see here is what's called a flanged and dished head. The ASME will require some sort of doming because being a pressure vessel. And this is a cold forming process, making this head. It's a series of hammering and spinning into this specific shape. With LDX 2101, you definitely need to be aware of the tensile and yield requirements, and typically you will have a more powerful machine to do this process. It does allow us, though, with the higher tensile and yields, to down gauge the material, and it definitely has made it practical. Edge preparation is an extremely important thing. It is with carbon steel as well, but it's absolutely critical that you don't want to have any heat or any sort of stress risers, sharp edges, or burrs that could impact it and lead to cracking along the edges. This is a cold forming operation that you're looking at here, where we actually are taking the LDX 2101 after it's been rolled into a cylinder and welded, that we're bending a 90-degree angle and impressing a D-ring groove into the unit. What we'll be doing here is actually creating a seat for a heat exchanger to fasten up to this flange. After the bending operation is done, you can see the D-ring groove. There are a series of holes that are punched into the metal that will allow for bolts to be passed through and connect the heat exchanger and the tank, or the tank flange itself. You'll notice the heat tint around the interior edge there. What you don't see in this picture is there is a backing bar that is attached to the non-water side of the unit to basically give more material for a bolting and compression and spread the load across a wider surface than just the tank flange itself. After this flange is constructed, then we are going to be attaching it to a cutout in a cylinder, and then it's going to be welded into place. So that large opening would be typically a manway, or where a field removable heat exchanger would be attached. Yeah, oops, sorry about that. PVI utilizes LDX tubing as well for heat exchangers, which inside the tube will be hot flue gases, and surrounding the tube itself will be the potable water. These rather odd shapes are cold formed, and when finished, these tubes are then applied to a combustion chamber, and it makes a very nice tight pattern that is then inserted into a cylinder to make a water heater. So this, what you see here, is a heat exchanger. And the advance is a little slow, excuse me. I don't know, it's gone back, pardon me. The use of bimetallic welding is also done at PVI here, where you would have a carbon steel tube sheet and LDX 2101 tubing. Again, hot gases are passing through the tubes, and the carbon steel tube sheet and shell of the pressure vessel would be then polymer coated for certain customers and applications. This welding that you see here is done on a welding robot, and we also do hand TIG welding in this type of process as well. ASME requires filler metals to be used and not autogenous welding. So what we end up doing here, corrosion resistance in potable water heating equipment is extremely important, and our TIG welding process, we actually over-alloy the welding wire, so when you're finished, the end result is the welding wire still has superior corrosion resistance, and 2209 wire is the wire that's been selected here at PVI. Cutting without the use of heat is very important in our product, and we utilize water jet cutting technology. So what we don't want to do is import a heat signature on the material itself, which would impinge and reduce its corrosion resistance, or require us to do a secondary operation to remove that heat damaged area. It's a very large water jet cutting machine. PVI makes up to 4,500-gallon water heaters. So actually on the bridge of this unit, you see two people standing there, kind of give you a size and scope. This has two bridges on it. Those are the big blue bars going across. One has a 3-axis cutting head, and the second one has a 5-axis cutting head. and jump frog. The 3-axis cutting head is used to cut with XYZ type of cutting. It's going to cut holes, it's going to cut slots into the flat surface to where we would be putting monitors or probes, things of that nature, or water inlets. The 5-axis head, is, I know Gary mentioned the need when it comes to joint design. And to minimize crevice corrosion, you'll see the 5-axis cutting head allows us to cut a compound bevel to minimize crevices that would otherwise impinge the quality of our product. These are 2,000-gallon water heaters that you're looking at here. And if you notice, you're going to see that there's brushing and the pickling and passivation has been completed on these units. PVI has a very large chemical processing facility, and it's been part of our history for over 53 years. When we went into the LDX 2101 production, we converted this facility to basically a very large pickling and passivation facility. And it provides the concentration of hydrofluoric and nitric acids that we use actually provides a better corrosion resistance of the material than when it comes from the mill itself. Just to give you a little size and scope of what we're talking about here, after it's been assembled, obviously we'll insulate and jacket the units, and they're actually quite large, as you can see. So water temperature is very important in our business. Some customers are requiring sanitation temperature water, and with LDX 2101, there is no real temperature issue in water heating equipment as long as it's within ASME codes. So as I mentioned, we call this entire process Aquaplex. I know Gary leaned on it at the beginning. We need to make sure that we're using a lean duplex LDX 2101 material, but with ASME codes, engineered joint design, proper cutting techniques, proper welding techniques, and immersion and passivation. All those really have to be done well to provide our customers a product that we're looking for, and we've adopted, with Outokumpu's help and Dr. Karinski's help, those methods and technologies. So to us, we can't compromise. Any failure in any one of these would lead to a failed product, and I'm very pleased to say that Aquaplex as a brand is a very, very good name. So at this point, I'm going to turn it back over to Jim, and thank you very much.
Great, thank you very much. I'm going to do a little wrap-up here for you, and then we can get with the questions and answers. One thing we want to stress here is we talk about the cost efficiency of stainless, and when we talk about that, we're talking about the maximum performance of the investment. A lot of time people get hung up on just, they ask you, what's the material cost? What is just that root cause of the alloy? But it comes to a bigger thing in our estimation. When we talk fabrication cost, as these gentlemen told you, a lot of times if you use duplex, you can design lighter sections. That's going to lower your fabrication cost and your initial cost. A lot of the operation and maintenance, if you're using stainless steels, you're not going to have to get involved with a lot of the cleaning that you're going to have to if you're getting into something with like a carbon grade or when you're going to have to paint it. You don't have to do that with the stainless steels. A lot of the design life of a project is involved here. The design life for stainless steel is much greater than, say, a carbon grade. Over here we're talking a lot with the environmental impact. Everyone's saying go green. Stainless is the way to go in that respect. We're waiting for the advance. Here we go. Here's some great knowledge. We have a lot of good technical knowledge available here at Outokumpu. We have our corrosion handbook, which is shown on the left. Outokumpu's been putting out corrosion tables back since 1934. We're into our 10th edition of the corrosion handbook. Last one was printed in 2009. What's unique about this piece of literature is it helps understand the different types of corrosion damage that can occur due to poor material selection. It's a great resource. Other handbooks and data sheets we have at Outokumpu, we have our welding handbook that was last done in 2010. We also have a lot of data sheets on the different grades and the properties available. We have machining guidelines. These machining guidelines and technical papers are available at our website, www.outokumpu.com. It's a great website. It is very extensive. I'll admit it can be a little overwhelming at times, but it has a nice little feature there. Just use the search box to navigate the site. It's a lot of great information there. Some other useful sites you can look at to go over some duplex. The one on the left there, that's the European Stainless Steel Development Association. If you go into there, they're going to go into a lot of materials and applications. They talk about industries, architectural, building and construction, transport, stainless steel usage in the home, and they have a section on environment and human health. Over on to the right, you'll see the Stainless Steel Industry of North America. They have a nice stainless steel information center. They'll cover finishes, corrosion, fabrication. They talk structural design, and they have information handbooks. The last one on the bottom is the World Stainless Organization. That is an international stainless steel forum. They'll cover sustainability, applications, publications, statistics, and training. A lot of good help on the websites of these different organizations. Last thing I'm going to cover is, this is a great slide. It shows some of the common standards and approvals that are relevant to duplex and to LDX 2101. You know, it covers the domestic ones that we use over here in the States, the ASTM and the ASME designations, along with the European specs, the EN specs. And then I'll kick it back. Thank you.
Thank you, Jim. Thank you very much to all of our presenters. We've got about 10 minutes left for questions, so go ahead and use that control panel question box on the side of your screen and fire your questions at our speakers. First couple questions are for Gary. First question is pertaining to laser welding. Do you need to use a filler metal when you're laser welding these alloys?
Yeah, typically the only one that seems to laser weld, again in thin sections, is LDX 2101. The problem is when you start welding some of these other duplexes without a filler metal. Again, when we weld, we want to try to be 50% austenite, 50% ferrite. When we do not use a filler metal, we're going to be highly ferritic in that weld. We're not really going to be a duplex stainless steel anymore. So to get the duplex structure, you typically have to use a filler metal. And with laser welding, people are using hybrid lasers, so it's a laser weld followed by something like a GMAW weld to make sure that cover pass does have the duplex structure.
Okay, great. Next question has to do with work hardening. Do the duplexes work harden similarly to austenitics, or is there a different
You're going to find with the duplex stainless steels, we have lower nickel content, and that's what really lowers the work hardening rate in austenitic. So when we have the duplexes, you're going to find we have higher work hardening rates, and that's why when I talked about forming, you tend to get more spring back in duplex than austenitic stainless steel.
Okay, good. A question for Chris on the carbon steel tube sheet. What was the reasoning behind using carbon steel rather than LDX? Is that commercial, or is there some other reason why?
Well, there are certain customers in this country, namely our government, who are very slow to change when it comes to specifics of materials, and while they don't have a problem with us using stainless steel or specifically LDX 2101 fire tubes, they're just slow to change from their 60-year carbon steel experience when it comes to dealing with shells and tube sheets for water heating equipment. It makes no sense, you know, but still it's a big customer for us.
Mm-hmm. Let's see, how does laser cutting compare to plasma cutting? These duplex materials. I don't know.
I'm going to pass that to someone else because we don't do either.
Gary, do you have a feel for that?
It's laser, and what was the other one? Plasma?
Plasma? Yeah, plasma.
Yeah, both of them can be used. It really depends on the thickness. When you get the thicker materials, you're typically the plasma is going to work fast, or lasers used typically on thinner materials. With the laser, you typically have a little thinner heat-affected zone than you do with plasma. PVI has gotten around both of these by using water jet cutting. That works very well because now we take the heat out of the equation altogether, and we have no heat-affected zone. So are used for cutting.
Okay, and I think this question, Chris or Michael, or both of you, related to springback when you're fabricating LDX 2101. Do you experience much springback? How does it compare with some other materials that you use?
Well, from the PVI perspective, it was definitely part of our R&D process. We find that springback is something that you end up having to expect and put into your design calculations, and it does, at the end of the day, limit certain things that you can do and certain things that you can't. So to calculate, I'm not sure what the exact number is, probably 15 to 30% depending on the what you're trying to do. And again, we tried to do some very complex shapes. There's certain ones we just said we couldn't do or shouldn't do. So springback is a reality here. And Gary?
Yeah, definitely. Anytime you're doing a bending operation, the other thing that's going to affect you is on the bend radius. Typically, you're looking at a bend radius of 3 times the thickness of the material. With other stainlesses, you could definitely get the tighter bend. So the spring back and the lower ductility of the material definitely come into play when you're cold forming duplex.
Okay, good. Chris, in regards to water jet cutting, how thick is the material that you're cutting with the water jet, and what type of speeds are you seeing?
Well, if it varies. Let me speak about speed. We will typically cut materials 1/2 inch and below regularly, and if you're using a single thickness of material, you can figure in a range of anywhere from 8 to 14 inches per minute. But depending with a water jet machine, depending on the distance between the port of the water jet and the bed itself, we stack material. We stack material 4 inches thick, and just changing your speed and feed, you can cut all day. We cut lights out around here is what we say. So it just, machine goes 24/7. So it really depends on what you want to do with it. It's all about the specification of your water jet machine, and that's really your pacing item.
Okay. And a question about when you're cold forming, carbon contamination related to cold forming. Were your dies dedicated to stainless, and how easy is it to prevent carbon contamination when you're working with LDX 2101?
Oh, anything that we do here at PVI, we basically have a completely separate set of materials and tools when we're dealing with carbon. I mean, there's complete isolation of tooling. Now, with LDX 2101, you're not as limited as you would be working with an austenitic material with carbon because of the ferrite content. But, yeah, we still, I mean, you're going to find there's no carbon steel hammers involved. We'll be using very heavy-weighted plastic hammers. But we also have the ultimate pickling and passivation facility that if there is any sort of impregnation, I assure you that stuff will eat it up.
Right. Okay. Question about annealing. Does it effectively relieve work hardening as it does with 304 and 316?
Yes. Yeah. When you do an annealing process at high temperature, it removes the cold work, and you get back to annealed grains very similar to you would with any other type of stainless steel. So, yeah, if you get something that's very hard, you can go in and anneal it, soften it back up, and then continue working. You've got to do additional cold forming.
Okay. Question for Michael. Was that sculpture mounted via one point to the wall, and how much did that sculpture weigh in the end?
structure weighs about 3,200 pounds of stainless steel. The bracket that it hangs on is another ton of painted steel, and yeah, it hangs from a bracket on one edge. The rest of it's cantilevered.
Okay. You mentioned a welding handbook. Is that available on the Autocompo website? Is that something that's downloadable?
Yes. The one that there's a URL on one of my slides that has the forming and practical use handbook, and that is available for download.
Terrific. Okay, great. We have a couple more questions. A couple more minutes for questions. Question about FDX 25 and 27. Those were mentioned during the formability discussion. Are those alloys in development? The question really is related to the composition and mechanical properties of those two alloys. FDX 25 and 27.
Mike, do you want to, Mike Obenoff, do you want to answer that?
Yeah, sure, Gary. I can't speak for the plate products, but for cold rolled sheet, those two alloys are in development, particularly in Europe, where we're doing some trials already with some selected customers, and we're hoping to bring it commercially to the States, but we're not there yet to bring it to the States, but we will be selecting some candidates for trials.
Okay, terrific. A couple more minutes for any last questions. Anybody? Question about the code, ASME code. Are all of the duplex grades from Autocompo approved for ASME code use?
When you say code, there's lots of different sections, so that's kind of hard to answer, but we are working on getting them in the codes. The older grades are all in there. The 2101 is now an ASME code alloy. 2404 is now in there. So there are some other newer ones that we're still working on, but it really depends on the section and the construction you're talking about and the coverage.
Terrific. Okay. All right, great. And I've been told that anybody that wants that welding handbook can email Mike or Jim, and their email addresses are up on your screen there if you want to jot those down real quick, and they'd be happy to help you out. Okay, that brings us to the end of our webinar. We're right on time. I want to thank Autocompo and in particular Michael at Pyramid Structures and Chris at PVI for joining us this afternoon to share their stories and showcase their very interesting applications. And thanks again to everyone on the line for attending today's program. We hope you found it to be a valuable experience. Again, please remember that an archive of the program will be available up on our website, metalformingmagazine.com, within the next day or two, so you can review what you learned today and perhaps share it with others within your organization. You'll get an email from us when that archived webinar is up on our website. So again, thanks to everybody for attending. I hope you have a wonderful afternoon, and you may go ahead and close your browsers now.